so much. Malia, if you can go ahead and join Jaden at the, what's that, 8s? Okay, I'm going to have to find that presenter mode later because we got to keep going.
Oh, here it is.
See, I knew I had it. Thanks. Okay. Really quickly, were some of us out on Friday? Because there was like 5 or 6 of us that never got started on the Mathia assignment. Were there issues with that for some of us, or we were just out? You were out? Okay. So remember, I did assign that Mathia assignment on Thursday. I get if you were out Friday, that's a lot of time that you're going to have to make up. But for those of us who were here on Friday, when do you need to have that Mathia assignment complete? Wednesday, before that test, right? It's designed to help you study. Hopefully, did we start to see a lot of overlapping concepts on the Mathia assignment from what we've done in class? So it is designed to help you with in-behavior, intervals of increase, decrease, all of those different things, using our understanding of polynomials to sketch those curves. Get that done before Wednesday. If you were out Friday, make sure you stop and let me know so I can mark that and not forget that. So I'll give you till the end of the week to get it complete. But the sooner you get it done, especially before that test, the better. It'll help you prepare for that test. Tomorrow, we're going to take the first 30 minutes of class to review and for you to ask questions or for you to work on what you need to work on for the test. So that's why I asked you to do the self-assessment on the proficiency scale. Maybe look back at it tonight and look at demonstrate your understandings that you've done to figure out, hey, do I actually understand this? Is this something I need to ask a question about? And so tomorrow will be dedicated time for those first 30 minutes for us to look at different concepts from demonstrate your understandings, check your understandings, even Mathia. So if you have questions from any of those things, be prepared to ask those questions tomorrow. We good with that? Any questions? Doesn't sound like there are any. Man, is it just like we have a long weekend? Is it just that it's Monday? What's going on? We're flat. Yes, thank you. If you have the video release form, that'd be great to turn in. Mr. Hobby, can you grab those? I guess I need to get those ASAP. I didn't even think about asking for those this morning. That's my bad. And I didn't send out a message to parents. I'll do that during second block today. So if you have the video release form, please get that out. Because I just have to make sure I choose videos that don't have people, I guess, that don't turn it in, but that makes things way harder. So please remember, I know that it's scary sometimes being on video, but 1, y'all been on video pretty much the whole semester. It doesn't have to be scary. 2, the assessment is not about you at all. It is literally about me teaching and how I teach, things like that. So please don't let that be a scary thing. Just get those submitted. Today, we got these tasks. We're looking at Lesson 2, Understanding Data in Context. That's what we started last Thursday. Please remember, I mentioned this last week. What we're doing in this task is not going to be assessed, but it is the foundation to be able to do the next task. Okay, so that's why we have to do this Lesson 2. Yes, we skipped Lesson 1. The only thing we needed out of Lesson 1 was understanding one-to-one functions, which we defined. If you missed Thursday, make sure you look to get that information. Then we're moving into Lesson 3, Transforming Nonlinear Data and Developing Models. This is the most important part of what we are doing. And I'm going to explain some details with that. I have a proficiency scale that goes along with that lesson and the next 2 lessons that we'll be working with. That's all based on that. And these are the concepts that we're looking at. Modeling linear data. So when we create these models, we're representing real-world data, so we need to interpret what the slope and the y-intercept are in the context of the problem. It actually ties very well into the average rate of change that we did in the last unit, and then interpolating and extrapolating. Don't worry about those terms yet. They sound scary. They're not. I'll explain them later. Linearizing data. So we're going to develop models for nonlinear data, because the fact of the matter is most data in the real world, it's not linear, not at all. And so what mathematicians have to do is they have to figure out models for those nonlinear sets of data, and we'll look at that in Lesson 3. Before that, though, I do want to actually bring up Mathematician Monday. We didn't get a chance to do it last week because we didn't have class or school on Monday. I found a really good one that I really, really like. Lonnie Johnson, still alive, famous inventor, mathematician, engineer, 120 patents, which is really impressive. And I just love celebrating phenomenal thinking and work, right? So he was an engineer for the U.S. Air Force, where he worked on developing the stealth bomber later for NASA's jet and propulsion program. Really impressive stuff. So like anybody can become a mathematician, and one of the things I love about talking about him is, as a mathematician, that taught him to think and develop ideas and go deeper. Like, math is not just about studying things that's going to apply in your everyday life, even though it did in his work and in his job. But he was able to use his mathematics to really drive his critical thinking skills and things like that. So like when we're engaging in mathematical concepts, it's not just about reproducing a process, a procedure, it's thinking. And he did some really fun stuff with his mathematics. He's best known for inventing the Super Soaker water gun. He also invented the toy projectile gun that became the Nerf gun. So, really cool stuff using his mathematical and engineering understanding. Foundation for that, I assume as a child, maybe even today, we still love a good water gun and Nerf gun. Okay, at least Drake's honest, or Drake is the only one in the class who loves those things. I'm hyped for when my son gets a little bit older so I can justify buying those things again. It's like weird when a 33-year-old goes and buys those things. Sorry, I had to think about age for a second. When a 33-year-old just goes out and buys a Nerf gun, but you got a kid and it's totally valid. So, I'm thankful for Lonnie Johnson and all the contributions he's made. Alright, so lesson 2, understanding data in context. So this is what we did last week. We looked at the Auntie's data set, right? So this was an artificial set of data. All the other stuff that we look at is very real world. But like if you're going to school, and I think it was all about making A's if I look back at the lesson 1. And so the auntie gave the person a $15 gift card to start. And then every month that went by and they kept A's, they got $50 more in gift cards. And so when we graphed that set of data, what shape did that graph have? What was it? Linear, right? And we were able to write an equation for that linear set of data because how much was it increasing each time? 50 for every month, right? And so what is that 50 every month in my equation? It's with the x. It's the m, it's the slope, right? So one thing I would point out, and I'm going to actually go ahead and show this to help establish, I've never done this before and I just thought about it, to help establish what we're going to do in the 2 tasks inside of this lesson. 50 what? What is that 50 representing? $50. Is it just $50 though? There we go, right? We want to remember context, right? So, for every month that goes by, his auntie or your auntie gives you $50, right? That's putting context with those numbers. Okay, but what was with that 50x? Plus 15? Because what is that 0 right here representing? 0 months, right? So 0 months in, what's that 15 telling us? You got $15 in gift cards, right? Notice, when we're interpreting these values, they're not random numbers, we're putting the variables with them for context, okay? If you take an AP stats class or any kind of stats class, you actually take time to interpret slope and y-intercepts just like this. So this is a good foundation for when you get into what's called bivariate data, things like that. But we're going to use that in this lesson. By the way, sorry, I forgot this. One-to-one function. What was a function again? Hey, you with me? Okay, what's a function? One input maps to one output, and only one output, right? So what was a one-to-one function? And each output is mapped from only one input, right? And so what new test, so like, what test do we use to determine if this is a function? Vertical line test. What new test did we learn to help us check graphically if it's one-to-one? Horizontal, right? So remember, vertical line, yeah, both of these are functions, sweet. But if I check it horizontally, are they both one-to-one? Which one's not one-to-one? The which one?
The left one.
Okay, come on, use better language with that left one. What is that left one?
The parabola.
A quadratic, a parabola, right? So we're going to talk and we're going to use this information later because there's a really important concept called inverse functions where we have to have one-to-one functions. I'll explain all that later. But we need to know one-to-one functions. So what type of function is this one again? Exponential. Is it one-to-one? Okay. So those are things we want to consider and we're going to use this information a little bit later. So remember we picked up the calculators, we started looking at, I'll just go to this here. So the very first task here, the real task that we're starting with, remember we're looking at roads and bridges, right? And what happens to asphalt as the asphalt heats up? Or sorry, concrete. This one's about concrete. What happens to concrete as it heats up? It's also in the task. We might want to get it out. Does anyone not have a copy of this task because they were not here last Thursday? I got extra copies. What? It expands, right? So when concrete heats up, do you need a, no, you have a copy. Do you need a copy? As concrete heats up, it expands. And so what happens when it gets cold? It shrinks, it contracts, right? And what could be the problem if concrete is expanding and contracting like that?
Too big, too small.
It gets too big, too small, but like, why would that be a problem? Let's think about this. Let's say you perfectly built a bridge, right? You have exactly the dimensions that you need. There's my bridge. And that concrete expands. What could happen if that concrete expands and is perfectly locked in where it's supposed to be?
Over the bridge.
It could what? It could fall because it could crack, right? Like it's pushing against the sides and it expands too much and it starts to crack, and then what happens? That bridge falls and people die. I mean, we don't want that kind of stuff, right? What could happen if it contracts when it gets too cold outside? Guess what? Same thing. Because think about it, if it contracts, it's going to pull away from these sides where it's anchored in, right? And then it can pull the bridge in and it can then collapse and people can die. So, have you ever been over a bridge? Have you ever felt it go clunk, 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 clunk every, like, I don't know, few feet? Never noticed that? Okay, a few of us have. If you never noticed it, go back over a bridge. Most of us, I assume, are 16. Some of us are driving on their own. Just go find a bridge in town. You'll feel it. And, like, I don't think it, I think they paved it. But, like, if you ever went down University Boulevard, like, way back in the day, you felt it all the way down because they had concrete there. And it was just like clunk, clunk. So they put spacers in between the concrete, right, every so often. And so like it's metal pieces where there's a gap so that when the concrete expands, it has space to expand, and when it contracts, it has that space as well. So that's a design for concrete, but it's built off of this idea. So we generally pour concrete at an average of 70 degrees Fahrenheit, and it tells us that typically 1 mile of concrete will expand nearly 2 feet if the temperature increases to 100 feet, and it will contract nearly 4 feet if the temperature decreases to 10 degrees Fahrenheit. And so that doesn't seem like a ton, but just a few inches can cause major issues, right? Now that is over a mile, most bridges are not a mile long, but it is still things that we consider. At least legitimately, when I was doing engineering, we had to talk about this. These were considerations with our materials and how we developed our bridges, things like that. So that's all fun there. And so what we jumped into was, and this is what I passed out to everybody, or sent out, we should have this, right? We have our data graphed here, and what are we going to do with that line? We're going to try to match it up to those dots, right? Try to fit it as well as possible. This is my last thing before I get you started on this. One, I want everyone to practice developing their own model, okay? But then I want you as a group to come up with what model do you think best fits the line. So remember, we're going to take our cursor, and when you move it into the middle, you see how it turns into a little cross? You hold down the center button, and that's going to allow you to move up and down. What is that changing about the equation?
The y.
The y what? There we go, it's changing that y-intercept, right? And if I go to the end, it turns into a circular rotating symbol. Same thing, it rotates. And so what's it changing when we rotate things? It's changing that slope, isn't it? Y equals mx plus b. Just because you said y, you now think x, it's okay, I'll forgive you this time. But we're changing our slope. So what I want you to do is, one, if you're stuck, there's only two of us, Mr. Javi and myself, talk with each other and help each other develop a model, and y'all talk as a group, come up with what model you think best fits the data. We're going to come back together in a few minutes. Get your model up on the board. It doesn't have to be perfect, it just needs to be close. What are our questions? Yes, ma'am, Peyton.
Oh, I was gonna ask if you come over here when you're done.
Okay, I got you. Does anyone not have this file yet? Did you log in, Malia?
I did.
Did you get this file? Okay. If you did not get this file, let me know. Shadidra, did you get logged in? Okay, so log in. It should automatically come back to you.
What's the username?
Remember, first letter of your first name, then your last name. So S. Collins, and then whatever password you made. Going once, going twice, sold. So, if I were you, I'd get up. A few of us trying to already fall asleep, but try to fit that line to that data, come to an agreement of which one you think is best doing that job. Get your models up on the board within the next minute or so. You had a question?
Yeah,
Thank you, Jaden. Okay, so I want to talk about a couple of things looking around the room. First things first, just for the sake of our future moving forward, is there anybody who is like super proud of like the model that they developed on their calculator? Just because we want one focal point. Anybody is like, yeah, I want to, like, this is great. Really? Nobody? Guys, like, it doesn't have to be perfect. Kristen, you like yours?
yeah.
Okay, so let's do this. The reason I ask is I'm gonna pull up, let's go capture, I don't wanna do that. I wanna go capture class, capture the whole class, bring it up. Alrighty then. So let's start with Leah. Okay, so Leah, here's your model. When I'm looking at Leah's model here, does anyone have one that like, yeah, I mean like first off, is that pretty good?
Yeah.
How do we know that's pretty good?
Because it's crossing a lot of points.
It's crossing a lot of points. A lot of those points are really close to that line, right? I would say it pretty evenly splits it. Does anyone have a model that they're like, yeah, that's good. I think mine's like a little bit closer to those points. Miles, you proud of yours?
Well, actually, no. Well,
Alright, we're gonna vote as a class. Let's see. Miles is bold.
No. I ain't
No. You can't back out now.
I ain't mean that.
What do y'all think?
Cheating.
Do we like Leah's or do we like Miles?
Not Leah's.
We like Leah better, so we're going with Leah's. I'm just kidding. So these four, I'll say this. For these 4 points, I like this model better. But for these 4 points, or these three down here, notice how they're all a little bit above? So I might go with Leah's over this one, but they're both good models. Anybody else like, oh no, I had a really good model? Nobody? We're all scared. Ooh, I really like Bella's.
Nice.
Notice with Bella's here, we got 1, 2, 3, 4, 5 points almost perfectly on that line. Yeah, I like that a lot. So I'm going to use this as my focal point for some discussion details. So looking around the room, a lot of us wrote f of x equals. One thing I want to caution, so looking over at the 8s, can we see a great mistake that we want to be careful about fixing? There's no x, right? Remember, when we write that function, we need two things. What are they? Starts with an I, and the other one starts with an O. Inputs and outputs, right? So we got our output. Make sure that we include the inputs here. 2x minus 4.33. Cool. And I want to talk about a couple of things looking around the room, looking at our responses. So first things first, notice, and I gave a little bit more hint on this than I usually do, but notice how in the scatter plot, it gives us a point to define what the variables are, right? So how did we know that temperature was my input? It's the x, right? X, and then Y, input and output, okay? Now, one thing, the only debate, the differences that I've seen is, was the temperature of the air around the concrete, or was it the temperature of the concrete? How are we deciding this? That's fair, that is valid information, right? Like the temperature outside probably needs to change before the temperature of the concrete changes. But what did the language of the task actually say? So going to task 2, concrete is generally poured at an average of 70 degrees Fahrenheit. Concrete tests have shown that 1 mile of concrete will expand nearly 2 feet if the temperature increases to 100 degrees Fahrenheit. Likewise, concrete will contract nearly 4 feet if the temperature decreases to 10 degrees Fahrenheit. So what temperature are they referring to? The concrete, right? The concrete is poured at. And so I'll say this, in terms of small details, I'm not going to hold that against anybody, but reading closely is important. It is the temperature of the concrete that they're referring to there, right? So a lot of good stuff. And so I would say that. I talked about this with one group. How are we going to know when the concrete has contracted? I don't remember who said it over here. I think maybe Leah. What were you saying?
I said when it's positive, wait, contract?
Yeah.
Oh, I said when it's negative.
Yeah, when we have negative values, that means it's getting what? Smaller, right? And if it's expanding, then we're looking at positive values. Okay, so from here, here's one thing I'm going to point out. I'm going to let you know. 2 things when it comes to modeling real-world data. If we say f of x equals or y equals, then that means when I type in, I'm just making this number up, but so that was 70, so maybe this is like 80 degrees Fahrenheit. That means when I put 80 into that calculator, whatever I get out is the actual amount of feet that was expanded or contracted. Okay. Is this point perfectly on that line? It's close, right? And so what I need us to understand is when we create models like this, it's not y equals, it's not f of x equals, we put this cute little hat on there to indicate that it's a predicted output. When we are modeling real-world data and the line, the function does not perfectly hit those data points, what do we put? Not just a hat. What was the language I said? Come on. Yeah, I said a cute little hat. Come on, like let's make it fun. Don't make it lame.
That's not cute.
A roof.
I think it's a cute little hat. Anyways, how often do you put hats on things in math? Never. So it's a cute little hat. Moving on. But what does that cute little hat mean? Or just hat if you want to be lame. What does that hat mean? That's my predicted output. Okay. Now, here's a thing that I'm going to change even here to help this make sense in the real world. What is the output again? The feet, right? So the predicted feet is equal to 0.062 times, what does that x represent again? It is the input, but in the context of this problem, it's the what? Temperature. That's how I would write that. And that's what you would typically do in a statistics class, because it's not x and y. It's not just a random function. It's representing the whole world. Now, if you want to do f of x, as long as you have the hat, I'm good. You can even do y hat. That's perfectly fine. But what I like to do to put context to it is I actually put the variables there. It's not just y, it's the predicted feet, and you do want to remember of expansion or contraction is equal to 0.062 times whatever the temperature is, minus 4.33. Okay? Questions about that information? How are we feeling about inputs and outputs? Kristen's like, I'm crushing it. Even though I hate the little hat, the cute little hat, I'm crushing it. All right, so here's what I want to do. I want to give you a few minutes to, say again? The second one? What second one? I'm sorry. It's not little enough for you. Boop. Is that better?
It's a little slanted.
You're a little slanted. Come on, go a break here. There we go. All right. Okay, so moving from there. what I want to do is I want to give you a few minutes to make whatever notes you need to make about the model, about what the input variable represents and what the output variable represents, and we're going to talk about slope and y-intercept in just a minute. I'm going to hold on to this equation to use in the future and refer back to. You can use your equation or you can use this equation, your choice, okay? So go ahead and make whatever notes you need to on this paper to hold on to about input, output, all that fun stuff. I want to bring everything back together. I want to talk about some of the details that some of us have got. So first things first, right? I want to point out what this group did. Same thing over here. They wrote the y-intercept as a what? They wrote it as a point, right? But let's talk about this. We need to think more about what we did. Zero what? What is that zero? Zero what? Zero something Fahrenheit. You're missing a word in there. Degrees Fahrenheit, okay. So at 0 degrees Fahrenheit, what? Is what good? Gosh. Focusing on this math. So at 0 degrees Fahrenheit, what? What is that negative 4.33? Expanding?
Wait.
Contraction?
No. What?
Are you referring back to the one y'all were working on or the one we're working on right here? So what are we working on right here? Well, dog, it's written there.
Oh, that box.
We're looking at the y-intercept right here, right? Okay. So 0 degrees Fahrenheit, then what? So what about the feet of the concrete? What about it? It has, Leah, what did you know about if it's negative? It contracts it, so it's contracted. Now remember, if we say contracted, do I have to say the negative? So it's contracted how much? I need a little bit more here. Feet. Technically, we'd want to add that detail of over a mile. So at 0 degrees Fahrenheit, because that's x, the input, the concrete is contracted that much. Ooh, actually we're missing something here. Don't forget, is this the actual y or is it the predicted y? So it's not that the concrete hasn't contracted that much, the concrete has predicted or is predicted, should say it that way, to contract 4.33 feet. Do notice I'm only putting the prediction on the output because the output is predicted off the input. So you put the input in, you predict the output. Okay? So, we're going to get another practice problem with this in a second, but I want to look at the slope here. So when I talk about slope, change in y divided by change in x, but again in this case, it's a predicted change in y. Please note, this is about change. And so, Miles, you all use the equation we have up here. So what is the slope right here?
0.062.
Okay, now is that the change in y or the change in x? Change in y, so what is the change in x? It's understood to be 1. 1 what though? What is the x? The x. So this is why I would always write it out, okay? So 1 degree Fahrenheit, but that's how much it's changing. 0.062 what? Feet of expansion. Notice all I did at this point so far is I put my input and output variables with those numbers. Now, when we write about it, we want to put a little bit more with it, but we would start with independent variables. So for every 1 degree Fahrenheit, is that increase or decrease? Notice I'm always going to need to talk about increase and decrease with slope. Is that increasing or decreasing? Is what, Shadidra? It is increasing. Why do we know it's increasing? Because it is If it's positive, for every 1 degree Fahrenheit increase in the, go back to that context, what temperature is increasing? Remember there's a debate about it. It was whether it was the air or it was the concrete. Which one was it? Concrete, right? So for every 1 degree Fahrenheit increase in concrete, then what? You're super close. You're super close. There's a really key word that you're missing. Is that exactly how much the concrete? That's how much it's predicted. Don't forget that output is a predicted, right? So the what? There we go. The concrete is predicted. That's a great question. Leah, what do you think it's going to be? Why is it going to be expand? Well, it's not just that. There's something else that tells us it's expansion. It's positive, right? If it's contracting, get smaller, positive is getting bigger. It's predicted to expand. Yeah. That's it. That is putting context. One thing I will point out is, if I'm trying to write it in context like this, I start here with my variables to make it make sense. I start with identifying my inputs and my outputs. Otherwise, it's really tough for it to make sense. Okay? How do we feel about that detail? Does that make sense? You good with that? Sorry. I know a handful of us are still making notes, but for the vast majority of us, I think we're done. So I'm going to leave those notes up there. But I want to look at the next question really quickly. The next question says, use the linear model to determine how much 1 mile of concrete expands at 110 degrees Fahrenheit. And so what I want you to do is I want you to just talk for a couple of minutes, and I want, or just a minute, come up with a strategy that you as a class, or you as a group, thinks would work. How could we use this equation to figure out how much that concrete will expand at 110 degrees Fahrenheit? Sound good? So just 1 minute, come up with a prediction of how we can do this. So how are we going to use that model to predict how much the concrete will expand? Say that one more time. With the slope? What is the slope though? I hear you. But, so you, I mean, I just want to point out, you say plug it in, right? But the slope is a number, so how are you going to take the place of a number like that? So, is that what you meant? Substitute in for x? So, yeah. Remember to keep in mind the slope versus the x strategy. What have we talked about? Besides trying to fall asleep on me. Oh, you're substituting. Got it.
Yeah, what's a prediction of that?
Talk with your group, guys. Talk about it. Okay. So, I didn't get a chance to talk to anybody on this side, so that's my bad. Sarah, Brianna, Peyton, what did y'all talk about? Did y'all come up with a strategy for how I could use these models? Nothing? You didn't even talk?
I mean, we were in the middle of coming up with something, but it wasn't finalized yet.
Okay, what were you coming up with? It doesn't have to be finalized.
That's the thing, we don't.
Brianna?
No, not. We're so scared to be wrong that we won't even try. Miles, Shadidra, Mary, did y'all come up with anything? Substitute? What?
Can we do that,
Okay, what would we substitute that 110 in for? In for x? One thing I want to pause and I want to remind you of, this is actually a key reason why I love this right here. I want you to think about this. Where's the only place that we could reasonably substitute that 110 in for? For the temperature, right? Not just x, but literally I wrote it with temp in there, right? And then what am I predicting? feet. That's why I love this model and writing with that variable in there. Go, it's 110 degrees Fahrenheit. So pick up your calculator, create a calculator scratch pad or add a new page. Yeah, so you can go to the scratch pad if you want or just add a new calculator page. How much does it expand or contract at 110 degrees Fahrenheit? Yeah. So remember, don't go to the next page. Take the time to add a page. Yeah, whatever equation you want.
We don't want to grab here.
Bro, the eraser failed. I'm just still the eraser failed.
So, because you put a, I don't know.
Okay.
You must have not put a decimal, you must put multiplication accidentally. So, using Bella's equation, I got 2.49. Did we get numbers close to that? Did anybody get something not even close to that? Just so I can help you. Okay, so notice, what does that 2.49 mean? In the context of this problem, what does that 2.49 mean? 0.62. So at 110 degrees Fahrenheit, the I want to point out some beautiful language with that. Is that exactly how much the concrete is going to expand or contract? No, not definitely not. It may be, but there's variability. We don't know, but it is, what'd you say on that one? Predicted to, why do we know it's expanding? Because it's positive. Okay, I want you now to find a prediction when the temperature is negative 10 degrees Fahrenheit. Don't forget, a beautiful part about these calculators is you can just hit the up arrow until that expression is highlighted, hit enter, and go change what you need to change. Now you gotta take that y out.
No.
See this y that you accidentally had right there? Yep. And then change your 110 to negative 10.
Okay.
No.
I don't know if I just redid that problem from like switched out the one thing to
Go to the scratch pad.
Look, I'm bored.
Board?
I did my homework.
Orange.
So we're just
Do you have a question, Stephen?
we're using this data. We're going to continue accessing. We use that model. We took time to interpret those slips. And I would say you see the information from Melissa, but she hates me. It's not on a test. She's not write it down. So I'll sit down.
I was out Friday.
All right. So how much? So at negative 10 degrees Fahrenheit, is that concrete expanding or contracting? It's contracting. How much? Now remember, if it's contracting, we're already indicating that it's negative, right? So we would just say it's contracting 4.95 feet. See, that could be a whole lot of problems if you're trying to build a bridge or a road or anything like that, okay? So, notice that's all it is. Now, the next piece is what's actually really important. I'm trying to decide if we're going to do task 3 or not. Nah, I need to get to the linearizing stuff. Yes, ma'am. Did you do negative 10 or negative 110? Yeah, doesn't the problem say negative 10 on here? Yeah, negative 10. I looked at it, I was like, it's a big number. That explains it though, right? Okay, so, again, keep in mind the context. This is again why I love writing the model like this, is because I can clearly tell the context for my input and clearly tell the context for my output. From here, the only thing left on this sheet is to talk about, is this model one-to-one?
Yes.
So is it one-to-one? So I'm going to pull this one up. Is this model one-to-one? And don't just say yes or no, give me some evidence. How do we know if this model is one-to-one? Okay, so if I do a horizontal line, does any horizontal line intersect this function more than once? No. That means each output is mapped from one input, right? Okay, so is this a one-to-one function? I'm going to go with a yes as well, but I do also want to caution, did you actually check to see if it's a function yet?
No.
So vertical line test, right? When we say one-to-one function, make sure you check vertical line test and horizontal line test. Each input needs to map to one and only one output, and each output is mapped from only one input. So make sure you check both. And I know like some of us are like, well, duh, Mr. Kinney, I already knew that, but make sure when you're talking about evidence, you gotta look at both of those, okay? Now, what I want you to think about is this last question on that sheet. What is the last question asked? After that one. Oh, sorry, the one before that. There we go. Calculate and interpret the x-intercept. So for the sake of time, we're going to move through this quickly together. But what could I do to find the x-intercept in this function? 0 for f of x. Okay, cool. I don't have f of x. What do you mean? Okay, so for my feet, predicted feet, all right, so 0 for my predicted feet equals 0.062 times the temp. You can also just put x if you want. Minus 4.33. So how am I going to solve this? Plus 4.33 on both sides. And then what do I need to do now? Divide by. So remember, I can use the reciprocal or divide, either one. All right, so. What?
I got 68.9.
So what is x?
68.
68.9.
Comma 0.
What is that? So degrees. Because remember, it was 0 feet. And what temperature do they typically pour the concrete at?
70.
So 70 degrees Fahrenheit roughly. The expansion or contraction would be about 0 feet, right? That's that idea there. Now, I want us to quickly, and the only reason why I really focus on this for a second is I want you to think about, why do we want this to be one-to-one? Can anyone think of a function that we've studied that would not be one-to-one? A parabola, right? Why might we want this function to be one-to-one and not something like a parabola? What would be the problem when trying to find my x-intercept if we have a parabola? You have 2, right? If it's one-to-one, we only have how many x-intercepts? 1. But if it's not one-to-one, we would have 2. And we would have to think about which one is correct and which one's wrong. And so, hold on to that idea for one-to-one functions. It's important if it's one-to-one or not when we start talking about the next set of functions called inverse functions. All right, Mr. Hobby. Yeah, can you help me out by, actually let's do this so we're more efficient. Bella, can you make sure everyone gets one of these? And Mr. Hobby, can you make sure everyone gets one of these?
Absolutely.
Yes, ma'am. Nope, never allowed to use restrooms for the rest of your life. Okay, just make sure you understood that one. Nope, that's lesson 2 as well. Lesson 3. Wait. Okay. 2 pages. Yep. Yes, sir. Which one? I already passed out the Unit 6 one? So I just wasted paper?
Oh, yeah, you already gave us this one.
Well, if you have an extra, just trash it. That's my bad. I know, I'm devastated. Alright. So, I do want us to quickly look at the proficiency scale for this unit on inverse functions. And we're just barely going to get into it. That's perfectly fine. And so, hopefully we're familiar with some of this foundational stuff. Have we heard the term power and exponents before? Yes, hopefully we're familiar with those terms. Have we heard radicals and radicands? Yes. Have I mentioned index of a radical? Yeah, I thought that might be unfamiliar. Here's the index. So, first off, what's my radicand in this problem? What is it? 47. Shadija, what's up?
She wasn't here for this, so that doesn't seem bad.
Oh, so she actually needed a copy of this? Mr. Hobby, you can come grab the proficiency scale for it.
Yeah.
Okay?
Okay, Devin. Why did you say that? I didn't know it.
Oh my god.
Okay, so what would be my radicand for the second radical? 4x minus 7. Remember, the radicand is what is underneath the radical. And then radicand for this one here, 270. So my index would be 4, my index would be 3, and my index would be 2. What do I mean by index? So it's not, now,
The outside.
be careful, because like, that's outside the root, right? So it's the number in the little crook here, little corner, and it's telling you which root it is, right? So this is not a square root. What root is this? A cube root. This is a fourth root. Yeah, and then you have fifth root, stuff like that. Why is this a square root? Why did I say the index is 2?
So that's obviously
So it's understood to be a second root, the inverse of a quadratic. Okay? So that's what I want us to recognize here. We have been practicing with identifying features of functions, and we're going to apply that into inverses. It actually works exactly the same, and then we need to be able to determine if a relation is a function or not. I think we've done pretty much everything there except for index, but that's pretty straightforward. Next, this is what we're getting into. This unit, this mini unit that's going to lead into what are called logarithms, is all about inverse functions. And so we have to determine if a function is one-to-one. That's a key foundational piece here. Hopefully, we feel comfortable to mark pretty much everything off here, and even that. So we're already at the foundation plus a little bit of target. But we've got to start getting into the rest of these ideas. These are all new things here. So here's the lesson, lesson 3. This lesson is going to focus on transforming data that is nonlinear, because we just looked at data that was linear. And I guess I should show this. Here's even an example. So this is the one we didn't get a chance to get to. No, that's not what I needed. Here's the example that we did not get a chance to get to. It's all about modeling linear data with more scattered. This is how the temperature of Earth has changed since 1990. What do you notice about how the temperature of Earth has changed since 1990?
It changed a lot.
It's increasing a little bit overall, right? But it's definitely increasing since 1900, not 1990. What else do we notice about this? Okay, shows that there might be some global warming. Let me ask this: is this as linear as the previous set of data? No, not really. This might be a model that's halfway decent. Notice it's splitting the data pretty well.
Can we have Kelly Menifee to the office, please?
She's on her way.
Thank you.
So we have that linear model there. It's not perfect, but it's there. But notice how scattered that data is.
Yeah.
The real world, super scattered data, okay? But even that is still somewhat linear. What we're about to look at is super nonlinear data, which apparently I forgot to open. There we go. And I'm going to send this out to the class. So first off, let me recollect that one. Next. Delete. Okay. And now I'm going to send this one out. Alright, did y'all get a new file? Okay, go ahead and open that file. And so, this lesson is going to focus on transforming data that is nonlinear, that is curved, in an attempt to make the data linear. We're going to talk about why that's important towards the second task. But first things first, we're going to go to that list and spreadsheets. And you can have some notes there about the list and spreadsheets. Notice I just kind of left it open. We had a whole lot more information there in the past, and it just got to be a lot. So first things first, right, 1.2. I'm telling you that it is nonlinear, but how can you tell that that height is nonlinear just looking at it? What could you do to figure it out? The table here. The height is nonlinear. So it's not constantly adding, is it? Looking at the rate of change, what is happening? It's constant. Is it constantly adding? No. Oh, now it is though. If this is constant additive, so we got a linear additive rate of change. So linear additive rate of change. So what kind of function are we looking at? Remember, exponential had what type of rate of change? Constant multiplicative, right? Linear additive, that's the idea of quadratic, right? Linear, x to the first, quadratic, x to the second. Remember that power increased one every time. So what else could we have done to figure out that this is not linear? So you could have looked at the graph, is all I'm saying. So what do you think, or what is this telling us that we could do to linearize that data there? What's it saying on the left? Yeah, how are we going to transform it? The square root of the height. So let's see if this actually does work. So going to linear, notice right here in the gray box at the equal sign, hit equals. And what are we trying to do? What does the calculator tell us to do? So make sure you go to gray box under linear, yep. Equals, what are we trying to do to that height? Take a square root. So hit square root, right? So control squared. So we're taking the square root of the what? Height. Now here's how you access this, right? Notice right above the number 9 is what three letters? Above 9 is VAR. What do you think that VAR stands for? Variable. Notice what's there? Height. So hit the word height and then hit enter. Let me know if you need some help with this. It says in the gray box. Hit equals. There you go. Square root. So control square. And then hit VAR for height, or find height in there. Square root of the height. No. Under linear equals square root of the height. Okay. Did it linearize our data? Did it make that data pretty darn linear?
Yeah.
Okay. So how do we know this is linear data now? Constant additive rate of change. Why do you think that that made the data linear? We took the square root of what type of relationship? What was the relationship here? This was, remember, it wasn't constant additive. It had a linear additive rate of change. So what type of relationship was it? So it was a quadratic, and we took a square root. What's the relationship between quadratic and square root? They cancel each other out because they're called what? Inverses, not opposites, right? Opposites only has that one meaning of the opposite of 3 is -3, the opposite of -5 is 5, right? Those are types inverses, but square roots and squares are inverses of each other, right? Okay. So, here's the last thing I'm going to do with you today to help you set up for tomorrow. Remember, tomorrow, though, what are we going to start with? 30 minutes of review and practice, and so you study tonight, use your proficiency scale, use your demonstrated understanding, things like that. Oh, pause. Actually, I got one more thing here. Just reminding you that tomorrow we're going to have 30 minutes to study, but we're going to come back to this. So, I'll go ahead and tell you, I can't see any data, so what do I need to do? I don't want to zoom out, I want to,
Oh, that.
so menu, oh wait, gotta click on, I actually gotta click on the graph. So menu, zoom, data, oh, I still don't see any data. So the issue is not the zoom. I have not actually entered the data yet. So how do I enter data on a scatter plot like this? So I still go menu, right? That's the button that lets me do cool crap. Then what? What am I trying to create? So a graph, right? What type of graph graphs individual data points? Scatter plot. So go to graph entry, go to scatter plot, and notice you can enter your x and your y. Now what was the x variable in this case? I think it was just x. Yeah, x stat. And then what was the original set of data? Height. So I want us to look at this. I'm going to hit enter. Is that perfectly linear? Now we already know it's not, but watch this. If I take my line and try to fit it to that, you see how it's kind of curved around that line? That's because it's non-linear. If it's curved around a linear model, it's not working out. But I can go and create a second scatter plot with my x stat and my linear. Sorry for rushing, I just want to make sure we at least see this before tomorrow. And notice this set of data is in fact very linear. Okay? So we're going to talk about why it's important to linearize tomorrow, but notice I can create a linear set of data even when it originally was not linear. And that's pretty darn close to y equals x. Alright, so please pack up, please pack, someone put the calculators up. Please remember to study tonight so you know what questions to ask tomorrow. Alright? Yeah, David, can you grab this card for me real quick? Oh yeah. Is anyone else who cannot get this? Yes, I think that was it. Elizabeth, you had a question? Who said Mr. Kenny?
Sarah.
Who was it?
Sarah.
Sarah, what's up? Huh? Oh no! Yeah. What is review?